Hi, everyone. Thank you for joining us. This is the Firefighter Cancer Initiative seminar series. Today, our presentation will be from our environmental sampling program. We'll give everyone just about 1 minute to log in and to get themselves settled before we begin. Okay, well, we'll begin. Just a few housekeeping items. There is a Q&A function in your Zoom. If you have any questions for the presentation, please simply write it in the Q&A section. I believe that you'll also be able to communicate with the panelists via the chat. But if you have questions, you can write them in the Q&A function. And we'll be taking questions at the end of the presentation. Again, this is the Firefighter Cancer Initiative seminar series, and this installment is our environmental sampling program. The environmental sampling program is led by Dr. Sylvia Daunert, who's here with us, and also Dr. Sapna Deo, who has also joined. And the presentation will be led by Dr. Jeramy Baum today. So I'd like to turn it over to him.
Thank you, Cynthia, for the introduction. So today I'm going to give you an overview of what we've been doing for the last couple of years, specifically also this year, related to the environmental sampling program under FCI. I split the presentation into three main parts. The first section focuses on our past work and accomplishments, just to bring everybody up to speed. So some of the slides some of you may have seen and some won't, but afterwards you all know where we are. And then part two and part three, I'll focus on two new projects that we've been working on this year and somewhat in year 5. So obviously through the Firefighter Cancer Initiative, it's known that firefighters have a high incident rate of cancer. Particularly, it's higher than in a lot of the general population. And Dr. Lee, who is also a member of the FCI, initiated the cancer linkage and registry and determined that specifically for colon, prostate, melanoma, and testicular and thyroid cancer, firefighters have an increased risk over the general population. And one possible reason for this is their chronic exposure to PAHs. Now, it's not one of their only risk factors, but it's definitely one that may be contributing to that. So we decided to use PAHs as a great proxy for exposure risks to carcinogens. PAHs are polyaromatic hydrocarbons, and that's just the abbreviation we use. And they're a type of semi-volatile organic compound. There are other risk compounds that we group into this, known as BTEX compounds, but for now we're just going to focus on the PAHs. And then another thing that's a little bit beyond the scope for this presentation, it's another project for under our ESP program, is what happens to PAHs after they're internalized. So looking at the exposure events, but we're also concerned with what happens when firefighters internalize PAHs and they're inside their body. For that, the studies are mixed, but for benzoate-pyrene, which is one of the most well-studied PAHs in that group, it's classified as a group 1 carcinogen. And it activates the xenobiotic metabolism, which actually results in PAHs becoming more reactive and more harmful in the body than the original parent compound was. And I won't go into too much detail here for this, since it's a really different talk. I can hold a whole talk on this. but the main routes of risk or damage to the body are through DNA damage, induction of the p53 protein mutant, and disruptions in apoptotic pathways, essentially causing tissue repair delays, and then overall increased inflammation in the body. Like I said, this is focused on documenting where the compounds are coming from and how the firefighters are getting them into their system. So for that, we developed what we call the contamination exposure cycle. And first point of contact with pHs is pretty obvious. It's at the fire event. And firefighters are actually fighting the fire. This is where pHs are made, and that's where they're going to see the highest level of exposure. And then next in the list is their turnout gear. After a fire event, it's on their gear. They bring it into the fire engine, then to the station. And then from the station, Dr. Gabon did some work early on with FCI using UV dyes to show firefighters how secondary contamination happens and how that may lead to further contamination down this exposure cycle from the personal vehicle, even to the home and children and such. So it was clear that pHs are present and that the firefighters are being exposed to that. But we needed to develop a few different methods to actually document this exposure and then see actual values. So we started off with a couple of different techniques early on. We're using particle counters, which measure suspended particles in the air, which are also harmful particles. And we found high soot particle count in the 0.2 to 5 micron range. These soot particles are either largely made of pHs that have compacted and reformed, and at a minimum, they absorb high amounts of pHs on the surface. So these high soot, finding high soot particle counts is very concerning. In addition to that, we looked at general VOC off-gassing, and we found high and elevated VOC levels in their gear. And then obviously that we wanted to see how does it happen in real time, or during specific events. So we started looking into passive samplers that firefighters could actually wear. And we came to these wristbands. Wristbands have been shown, or silicone at least has been shown in previous literature to work as a absorptive material for different compounds and also pHs. And our question was, would it also work for the specific firefighter environment? It needed to be simple to use, cost effective, and obviously non-invasive to their behaviors when they're at a fire scene, and then be able to handle these harsh environments. And we actually published some work on this, demonstrating that the wristbands are in fact useful for documenting pH exposure for firefighters. And other work in our group, we also published that there is elevated exposure beyond that expected in normal areas outside of a fire event. This is just a quick rundown of the methods that we use for the wristbands. So we buy commercially available wristbands off the internet. They only cost a few cents, so they fulfill those previous requirements I mentioned. We treat them with different solvents. Then we vacuum and clean them, make sure all the solvents are removed for at least 16 hours. Then they go in their individual clean, controlled vials, and they're distributed to the firefighters for use. And then wear them for 24 hours, put them back in the vials, label them, send them back to us. And then the wristbands undergo a series of solvent extractions, followed by evaporation and preparation for GCMS analysis. And then we get spectra to show the compounds. And from that spectra, we generate these pretty heat maps that tell us the different exposure. So coming back to the exposure cycle, I pointed out the different spots that we're investigating. So the first one after the fire incident was the gear. The graph here on the left shows the different exposure for silicone bands that were placed with gear. Each column represents one set of gear, and then on the rows, those are the different pHs that we analyze. This is not all inclusive. These are just the compounds that we were looking for. So there can be potentially many more compounds. But what is important to point out here is as the color gets warmer, there's an increase in concentration for each of the given compounds. And if we average those out, so look at the cumulative pH exposure on the graph on the right here, and stratified by gear that was not recently used in a fire versus gear that was in a fire, you can see there's a the increased difference between non-exposed gear and firefighter exposed gear. And here on the right is just a picture of firefighters that have been adopting new decontamination practices that have been developed through work from the other teams in our FCI program. And that was like one of the sampling events that we were at. Next on the list were the stations as a potential exposure source. So again, the same setup. We distributed passive samplers throughout the stations and looked at the exposure levels. Obviously, there's no fire incidents because it's just the station, but we see the levels of pHs that are present at a given station. And if we sum that up and look at this distribution for cumulative pHs, you can see it ranges a lot from station to station. We go anywhere from 15 parts per billion all the way up to 600 parts per billion for a station. And this is early on we were looking around where we think exposures come from. We actually found soot inside the ice maker from one of the stations. And combining this work and some other air studies that we did in stations, which I'm not presenting today, we presented this to firefighter leadership in a couple of the stations and actually led to improved safety protocols and even the installation of some filter systems. And in addition to just pHs, we found more VOCs, phthalates, saline, and other pH derivatives that were floating around at very high elevated levels inside the station. The next on the list was the work assignment. So we wanted to look at when firefighters are at a scene, if they're not actually engaging in the fire, or if they are engaging in the fire, how does that affect the exposure rates? And for that, we went to controlled burns, because that gave us a unique opportunity to know the material sources, which you'll understand in a few slides why that is important. But it was good for us to know what are the burn materials that are producing the actual pHs. So from that, the setup was pretty straightforward. I guess I should tell you a little bit about the zones for the non-firefighters that are on the call. So when a firefighter arrives at a scene, or in this case, a controlled training burn, they divide the fire scene into the hot zone, warm zone, and cold zone. The hot zone is considered immediately threatening to life, while the cold zone is considered safe, and the warm zone is an intermediate of that. The warm zone is interesting to us, and immediately outside the warm zone is very interesting, because in those two zones, firefighters don't necessarily have to be wearing their personal protective equipment or that they're on clean air. So we wanted to see, analyzing these scenes and the different ranges of distances from the fire, can we establish something that can be used for guidelines to reevaluate these zones based on long-term exposure risk, not just immediate risks to life. So for the experiment, we laid out, in this scene, we laid out different samplers as shown here at different distances, all the way into the cold zone. And for the day, the prevailing wind was southwesterly, I believe. But you can see it's going away from the samplers. And this is just a picture of inside the warm zone, one person on air and another person not on air. And this is what the actual distribution of the samplers look like. We presented them at roughly chest height to simulate the firefighter standing there for the whole incident. And this is the results. I know this looks a little bit complicated, but we put the data into what's called a radial heat map, and the darker colors indicate higher levels of cumulative pH exposure. We also stratified this by heavyweight and lightweight pHs. I mentioned the soot particles in the beginning, because heavyweight pHs and lightweight pHs adsorb differently to particles. So then they take on a more particle-like behavior in the gas phase versus a chemical behavior in the gas phase. And that turned out to be correct. So you don't just get a linear reduction as you go further from the fire scene. You have a difference in concentration in different zones. But the main thing to point out here is the warm zone had a concentration of 160 ppb and the cold zone had a concentration of 175 ppb. Both are concerningly elevated levels, and there's no real good comparison based on federal guidelines or any national or even other international guidelines. The closest thing that we could use as a comparison is from OSHA. It's the 10-hour recommended exposure limit, but it's for CTPVs, which they're called coal tar pitch volatiles, and it's the amount of organic compounds that can get dissolved into benzene from the coal tar pitch volatiles. So it sounds really complicated, but the thing is that that level is at 3 ppb, and it's not 100% PAHs, but if it was, that would be the best case or the worst case scenario would be a maximum of 3 ppb total PAHs, and we are threefold higher than that. So both these levels are concerning. And then next we looked at firefighters in their normal everyday career activities. And the focus was to see the difference between firefighters that went to fire calls and those that did not. The graph on the left shows the individual compounds that we looked at. Green is for firefighters that wore the wristband but did not respond to a fire during their shift, and red is for the bands that did that were in a fire response. And on the right, we have the cumulative, so the sum of the PAHs that were on the wristband, not by individual PAH. And you can see there's a strong statistical difference between fire exposed and non-fire exposed. And I added in this dotted line here. This is some preliminary work that we started on in the beginning of the pandemic, so we haven't really been able to complete most of it. But firefighters showed a strong interest to see how do their wristband exposure profiles compare to those of non-firefighters. And that data just isn't out there. So we started to work on that and try to collect that information. And then the pandemic came. So we were able to collect some non-firefighter wristbands, and this is where the average fell for them. And you can see that's 2 times lower than non-firefighter exposed bands. So even firefighters that didn't respond to a fire call still had double the exposure over non-firefighters. And then obviously if they went to a fire event, it was even higher than that. Lastly, we wanted to figure out the different sources that contribute to the PAHs. So when a firefighter is at a fire scene, the combustion is present of the burning materials, and that produces a pH ratio based on the formation of the compounds in that given environment. And kind of adopted this technique from environmental sciences. So they use this to analyze pHs in streams and in soil from either like forest fires or factories and things like that. So you can use these ratios to then forensically, in a way, deduce where the exposure came from. So I won't go through everything that is possible from these ratios, but I'll just point you here to the highlighted sections. So the highlighted sections in orange show where the majority of the samples fell. X's stand for wristbands that were used by firefighters but did not respond to a fire incident, and the circles represent wristbands that firefighters wore and responded to a fire incident. And the takeaway from all these ratios were that the majority of the samples, regardless of incidents, response or not, fell in the zones for the ratios related to diesel combustion. There was also normal, like generalized combustion compounds, which makes sense, but the majority came from diesel combustion. And the other big message here is, I mentioned benzoate early on. The only true regulatory guideline I could find for pHs, whereas for benzoylpyrene, and that's one of the EU guidelines, they put it at 1 × 10⁻³ parts per billion. And remember, our exposure limits were in the hundreds of parts per billion, so 3 orders of magnitude higher. And for a comparison in the US, looking at all different cities and checking the literature for the levels of benzoylpyrene that they've found in cities, they also fall around 1 × 10⁻³ parts per billion. So those are very, very high exposure limits. So the need for a real-time sensing system was pretty obvious at this point from our passive sample testing. So we looked, does anything commercial exist? And firefighters do have real-time sensors for commercial monitoring, but they're usually for acute risk compounds like hydrogen cyanide, carbon monoxide, and they do also do some organics, but in the ppm range, not in the ppb range. And we just couldn't find a sensor setup that we needed for this scenario. And so we said we came up with our sensor design, and this was one of the first times we used it in the field. We went back to a controlled burn. That's just a good setup for us, and we affixed it to or close to the structure that was going to be set on fire. And we immediately realized this was not going to work. Our sensors were getting saturated. They were made for detection levels of much, much higher sensitivity than what we're seeing here. They were completely overexposed. So we knew we needed to get these mobile, but because it's inside the warm zone, we weren't allowed to move the sensor after the fire had been initiated. So the next obvious step for us was to mobilize our sensor, and we made this guy here called the rover, and that allowed us to maneuver the sensor throughout the warm zone during controlled burns and get different readings to provide information that we needed to improve our sensors. And that brings me to part 2 of this talk, where I want to show you the advances we made in our real-time sensing system, which ultimately will provide firefighters real-time information for their carcinogen exposure to hopefully limit their exposure, since it'll allow immediate intervention of the exposure event. In year 5, so that's last year, we started working with Chief Quintela, and we came up with the concept in-house, presented it to him, and then asked for feedback of what firefighters need, like what are they looking for in a device that's going to warn them of non-visible or risks. And this is the concept we came up with, and then we integrated it into an EMS bag. And right here you can see the 3D printed device here on white. Kind of over-engineered it in the beginning. I was warned from the firefighters themselves that they can treat gear pretty rough at times. So we made this very durable to protect the sensors inside, and it made it difficult for them to access the battery, and there's a lot of steps involved. So the first goal from this sensor setup was to just get it out in the field, get it in the hands of those that are actually using it, and then get feedback for them. So every operator that had this on their truck filled out a survey with lots of questions related to how they felt about the sensor. Does it complicate their task load? Did it provide any useful feedback to them? It didn't at first, but if it would provide feedback, what would they want? So for the first iteration, we didn't allow the firefighters to see the data output, because I don't want them to get concerned about a reading that isn't validated yet. So we just collected the information for ourselves, but it was, like if it was a running system, how would they like it to be? We got that information back, we reviewed the surveys, and we started working this year on the second design. And the first big change for us was in his district, they didn't use EMS bags. So they used airtight Pelican cases where they kept all their medical equipment. And that posed a problem in the beginning, since our device was put into a bag, which allows the permeation of gases and equalization of pressures. So we definitely needed to test it in the Pelican case. So we got a small Pelican case for starters and started putting in the new equipment. And some of the big points that they wanted were easier battery changing and battery replacement, so the plugs, and less invasive to the firefighter routine. So we had them, turning off the switch. They didn't know when the battery died. All these things we wanted to remove in phase 2. So we put in the battery. Now it's just with Velcro attached inside here, and then the electronics are contained on the side. Now this is still a prototype. The final version will not be in its own Pelican case. It'll actually be integrated into their Pelican case, which I'll show in a moment. And then I'm not going to get into all the details of the 3D printing and how it works, but it's very tedious. When we make a little change, we have to remake all the device parts in a 3D printer, test the functioning of it, and then repeat until we arrive at a new working model. And then we hand it back out. So here on the right, this is a picture of a large Pelican case, roughly equivalent to the EMS Pelican cases that I looked at. And I just put ours inside of it so you can see. So for the working version, this would not be in its own case. It would be integrated into their Pelican case for seamless workaround. They can just put all their gear on top of it and around it, and it wouldn't interfere. We also anticipate that the third version will be at least 40 to 50% smaller. And that's based on the electronics here. You can see that this is the old electronics that we use. There's lots of wires, multiple components that are larger. And then here on the right, this is the new setup, very compact. The board's all stacked. There's no more wires. The only wires that actually be inside the device will be the leads going to our gas sensors. And this is ready. We just need to get it back out in the field with Chief Cantella. So that brings me to part 3. All this work was started through our passive monitorings with wristbands, but we want to improve on that and expand the type of sampling we can do beyond just pHs. Even though they're a good proxy, they still don't provide a full picture of the exposure risk for firefighters. So the next one on the list, and this has probably come up in media and it's also more prevalent in literature, are PFAS, which I'll talk about more. So since the wristbands are commercially available and they're already made, it's limited what we can do to them to modify or augment their absorption capabilities and behavior. So we need to get away from the wristband and go to something that we could control more. So for that, we decided to go to tunable silicones, which in other fields, the literature has shown you can control the pore size of silicone while it's being polymerized. So to test that, we 3D printed a little mold and poured out different types of silicones and then exposed them to pHs to see how they would react. And the hypothesis was, if we can control the silicone porosity, that should lead to changes in the absorption characteristics of the silicone, and obviously, hopefully, improved absorption characteristics. On the bottom right, you can see a scanning electron microscope image of 3 different types of silicone that resulted in 3 different pore sizes. And this was published by a group that was using this for biomedical and drug delivery purposes. So they were loading the holes with reagents afterwards that were going to be given off. So we still have to check if the final version will actually yield those improvements that we're hoping for, but we're very confident. On the right here, you can see this is a quick schematic of how it works. So you mix up your liquid silicone and you change the solvent and wax ratio. So it's an additive that we put in there with the silicone, mix it together. And during the polymerization phase, these additives will then form small micro droplets and then coalesce to different size droplets depending on their mixture ratios. And once the polymerization is complete, we have our hard silicone. We can remove the wax, resulting in these little holes, essentially generating a micro sponge similar to the SEM image. And with that, we hope to be able to tune the silicone to increase the range of the semi-VOC capture beyond just the PAHs. And this is fresh off the press, more or less. We've been working on this the last couple of weeks. This was our first round of silicone testing for the different materials. For this, we made 2 different types of silicones and exposed them 30 minutes to 80 ppm naphthalene gas environment. And they seem to saturate at around 30 minutes. So this one here on the right shows at 60 minutes, there's no change in concentration. If you go from type 1 to type 2, you can see there's a change in concentration, suggesting one of them has a greater absorptive capacity than the other silicone. And that's good news. That's very promising for us. So the first thing to say why it's promising is the current wristbands that we've used at similar exposure events will saturate at 10 minutes. Now, this exposure concentration is much, much higher than what firefighters are going to experience in the field, but we still need to find out, what are our upper limits here in terms of concentration. And I also want to point out, we've only done differences in cross-linking. So this is only one step of the different silicones. We still haven't even added the pore size control. So we're already seeing differences that are this great just by changing the cross-linking of the silicone. So that was pretty exciting. And with that, we're going to go to the expanding of our testing library. So with those new silicones, we hope to be able to test new compounds. And one of those are the PFAS, as I mentioned in the beginning of this section. The PFAS are compounds that have been around for a while, but they have gained more attention lately. They're known as forever chemicals, and that's because they're fairly persistent in the environment. They also bioaccumulate, and they pose different risks to humans, and some of those being reduced immune function, and they've also been linked to different cancers. And of course, for firefighters, it's interesting, how are they exposed? Unfortunately, their own fire retardants are exposing them, so in their turnout gear, but then also at a fire scene, the burning or smoldering furniture, smoldering material, burning building materials, all these things have fire retardants in them. And once those things do finally start burning, these fire retardants start to come off in the gas phase or in the soot. And then also the firefighting foams themselves contain various PFAS materials. Some of these compounds have already been outlawed or removed. So whenever a new flame retardant is deemed a health risk, companies come out with a new one. And one of them is like Gen X of the firefighting foams. And you would think that's an improvement or healthier or less risky. But unfortunately, during the breakdown or the metabolism of some of these compounds, you still result in a PFOA, which is one of the PFAS that are no longer allowed to be used. So for us to analyze these compounds, we need to come up with a derivatization method to analyze PFCA with our current devices that we use for our wristbands, being GCMS. So the derivatization method is fairly straightforward. We have our original PFOA, which is non-volatile, so it doesn't go into the gas phase readily or at normal in a normal environment and atmosphere. And we treat it with isopropyl alcohol with sulfuric acid, and that yields an ester which is more volatile and can be found on our instrument. And the instrument itself also has to be tuned for that. So once we made the ester based on literature from Langlois, we still needed to check if we actually produced what we wanted, and the efficiency at what we're producing it. So the efficiency portion still needs to be investigated further because we have only done the qualitative work on that. But we were very excited when it actually showed up on our GC. So here on the right, you can see this is the GC chromatogram for the PFOA ester. And here on the left, this is the ion, the reference ion. That is really good news. So that means we did make the compound of interest and the derivatization method works, and the initial GC method is also functional. We still need to improve on the derivatization method and properly quantify so we can calculate the efficiency of the reaction. And we need to develop and work on increasing the sensitivity for the PFAS at lower concentrations that we think the firefighters are going to be exposed to. And this is a quick flow chart of how we see that working. So we have the different samples. We've tested this in a perfect sample matrix, and we need to move to the textiles that have the flame retardants, different plastics and silicones, and then soil and potentially also building materials. Extract those, clean them up, derivatize if there's PFAS present, so derivatize the unknown amount of PFAS in there, and then run it on the GC to get the report. And then that would open the way to expand our library. So there's, I only spoke about a few of the projects for today for ESP, and I just wanted to give some highlights for the milestones. So tested the methods and analysis for PFAS, and this will help with the expansion of our library to give a more complete exposure profile of firefighters. And we've also worked with new silicone materials and to yield an improved passive sampling device. That's still ongoing, but it's looking very promising with our first 2 silicone types that we've worked with. Then over the course of year 5 and this part of the year, we've been able to improve on our sensor of our real-time sensor system based on firefighter feedback and our own experiences. So that second round or iteration of our device is ready, and we just need to get back out in the field. And then this is another section I didn't talk about at all. It's a big project. One of our other grad students is working on it. It's using advanced solvent extraction methods for urine and vaginal swabs. So they're looking at the fate of pHs after they've been internalized. That is really close to being finished in the final optimization phases. And then I was really excited to announce that we've published a new manuscript on firefighter pH exposure, which was the first section of the talk, documenting how the situations in their environments are affecting their pH exposure. And with that, I'd like to thank everyone that tuned in and was listening, and obviously everyone that made this possible. So on the top, we have the Daunert Deo lab, which is a big research team, and then everyone down here from FCI that's involved. And I think with that, I can open up the room to questions.
Thank you so much, Jeremy. I believe that we do have one question in the Q&A. It's from Keith. He said on slide 11, it shows more PPB than warm. What do you contribute that to?
That is due to the particle binding behavior. So in the fire environment, there's that, I think it's called a heat vortex, and the particle bound pHs are going to drive up into the vortex differently than the non-particle bound pHs. And when these compounds that are on particles and not on particles start to diffuse and travel further away from this extreme heat vortex, they start to behave differently. And I think the the weight of the particles is going to make them fall out more. So that's why we're seeing a difference in the zone.
Thank you, Jeremy. As a reminder, if you do have any questions, you can submit them via the Q&A function at the bottom of your screen. We'll give it one more minute in case anyone has any other questions, or if anyone else would like to comment from the panel, you're welcome to do so.
You know, I just would like to say that I am very proud of our team, and you know, we are very excited about this project, because when we see that our research can have an impact with such a wonderful community as the firefighters, it really is very exciting, and really shows that at least we're trying to contribute a little bit to improving the health outcomes of our heroes. So thank you for letting us be a part of this incredible program.
Thank you so much for that, Dr. Daunert. And if there are no more questions, I'd like to say thank you so much, Jeremy, for a wonderful presentation, Dr. Baum, and Dr. Daunert and Dr. Deo for all of your wonderful work, and for the collaboration, and for everyone who's listening. As Dr. Daunert said, we couldn't do it without the firefighters that we work so closely with and in partnership. And it is very special research that we're doing at the Firefighter Cancer Initiative. So thank you all for all of your contributions. I would like to give a few reminders. I'm sorry, Dr. Daunert, did you have something else?
No, I just wanted to thank you for managing this series and everything that you managed for us so well. So thank you, because without someone like you managing the program, it wouldn't go. So thank you.
Thank you very much. I appreciate that sincerely. Thank you.
I have to second her on that. Thank you. Yes. It's a great opportunity to be able to present our work. And that's, you have to have the audience to be able to do it. So it's very rewarding.
Thank you so much. I'm very proud to be a part of this team, definitely. So with that, our next seminar is going to be on January 28th. We're going to be having Hannah Kling will present Total Worker Health with Dr. Alberto Cabana-Martinez's work as well. So we're definitely looking forward to that. I would be remiss if I didn't say happy holidays to everyone that's here at our presentation today. We wish you a very safe, healthy holidays and a good new year, definitely. And just a couple reminders, this presentation will be posted on the Sylvester Comprehensive Cancer Center YouTube page. We have a playlist. The Firefighter Cancer Initiative has a playlist with all of these presentations that we've had for this seminar series. So if you go to the Sylvester Comprehensive Cancer Center YouTube channel, if you go to playlists, there is a Firefighter Cancer Initiative playlist where you'll be able to view all of these. And please also follow us on social media at FCI Fights Cancer for the latest updates, and also links to our presentations and our research. And with that, I'd like to say thank you very much. Thank you for all the presenters and for the lab and the team and all the work that you do.
Happy holidays to you too, Cynthia.
Thank you.
Bye.
Bye. Have a great day.